This tutorial serves as an introduction to SPICE. Unfortunately, it doesn't cover all the different software packages that are out there. We're not going to talk about Cadence. We're not going to talk about multisim. And unfortunately, we're not going to talk about all the different simulation types or modes. Now, we actually are going to talk about the different modes. We're just not going to demonstrate how to implement all of them. We're going to focus on DC sweep, although we'll talk briefly about transient and AC sweep analysis. However, I think the main point here is that this document will provide you an introduction to the simulation of basic DC circuits via SPICE and LTSpice. Now, why do I focus on LTSpice specifically? Because in my opinion, it's one of the better free tier circuit simulation or SPICE-based circuit simulation packages out there. It's pretty robust. It doesn't have a lot of restrictions in the free tier, which is a stark contrast to something like the OrCAD free tier. Overall, I think it's a great starting point, and it seems to be very popular with students, so I decided to formulate the tutorial around LTSpice. So I'm hoping that this will serve as a jumping off point for those of you that are interested to do some independent learning and exploration of different circuit simulation options. Like usual, I am going to provide an external YouTube-based resource that's related to this, so I'll post the link in the description. You can check that out on your own. Now, what is SPICE and how is that different from LTSpice? So, in the most basic terms, SPICE is a family of algorithms or a family of simulation programs that can be implemented in different ways by different companies, and that's why we have like multisim, OrCAD PSpice, and LTSpice, and a large number of alternatives. So SPICE stands for Simulation Program with Integrated Circuit Emphasis. It's a general purpose, open source, analog electronic circuit simulator. It's a program that is very heavily used in integrated circuit and board level design to check the integrity of various designs and predict circuit behavior. Essentially, SPICE software allows us to design a circuit and simulate how it would behave in real life. For example, it may calculate the voltages at all circuit nodes within a schematic, and that's what we're going to be doing here. If you realize, and I know that many of you have not looked at the later modules yet, but solving for the voltages at the nodes is pretty much the same thing we're going to do when we jump into nodal and mesh analysis. So it's an alternative to that. LTSpice is a SPICE-based circuit simulator, implemented in software, obviously, that's produced by semiconductor manufacturer Analog Devices, which was originally Linear Technologies, hence LTSpice. It's one of the most widely distributed and used SPICE software packages in the industry. Like I said, it's always traditionally been very popular with students. Though it's freeware, LTSpice is not artificially restricted to limit its capabilities. So there's no feature limits, no node number limits, no component limits, no sub-circuit limits. It also ships with a library of SPICE models from Analog Devices, Linear Technology, Maxim Integrated, and various third-party sources. If there's one disadvantage of LTSpice, I could say, is it has a little bit of a smaller component library than others do. But the nice thing is we can always import other models, new models, and even create our own models and import those into LTSpice. So this tutorial is going to focus on LTSpice because it's a good option. So the objective here is going to be to demonstrate how to perform a DC sweep simulation or analysis for the circuit that's shown below, right here. This circuit is introduced in one of the other lectures. We haven't gotten to that yet, but it's composed of two sources. So we have a current source and a voltage source with their respective values. And then there's 4 resistors, 1, 2, 3, 4. As part of the later lecture, which is on nodal analysis, we actually solved for the voltages between nodes A and D, B and D, and C and D. And we call them VA, VB, and VC respectively. So we know what the answers are that we're looking for. We expect VAD to be 0.7835 volts. We expect VBD to be 0.7679 volts, and we expect VCD to be equal to 1.25 volts. And I don't explicitly show it, but I'm expecting your ground to be there, since it's automatically or already being assumed to be the reference node. So our DC sweep, what it's going to do is provide us with that value as well as a variety of others corresponding to IS ranging from 100 to 150 microamps. So let's talk real quick about the nature of a DC sweep and the kind of output we expect to get. So let me draw a little graph here. Okay, on our x-axis we're going to have an independent variable which is IS1. Now, that's going to range from 100 microamps to 150 microamps. In the middle is the 125, which is the nominal value that we calculated for above. On the y-axis, we're going to have all kinds of different values. Predominantly, it's going to be VA, VB, and VC, which is the same as VAD, BD, and CD. And then what we should expect to see are different lines here that correspond to the values of VC as a function of IS1. And we'll be able to click on specific points and look at specific values associated with our x-axis. So we'll be able to look specifically at what are those values when IS is set to 125 microamps. But the reason why it's called a sweep is because it's going to sweep from left to right and give us a whole range of values. So again, this is the circuit that we're going to be using right here. 2 independent sources, 4 resistors, and 4 nodes, A, B, C, and D, with D being the ground node. And we already know what the answer is that we're looking for from right there. So now that we know what circuit we want to simulate, let's actually start building it in LTSpice. The first thing that we're going to do, and this is really in no particular order, is place the current source, then we'll place the voltage source, then we'll place the resistors. So this tutorial, unfortunately, is not going to discuss how students can install and open LTSpice on their machines. Generally, whenever I include material like that in a tutorial, it goes out of date, it becomes obsolete faster than one would believe, and so it really is a detriment to the tutorial. So I'm going to suggest that you explore some online resources for assistance with this task. It's pretty straightforward. You shouldn't have to pay anything. You download the installer and then follow the instructions. So assuming that we can open LTSpice on our Windows machine, we're going to go to the File tab in the top menu and open a new schematic as shown right here. So new schematic. And that's going to open up a space where we can essentially build our circuit. All right, next. After that, we go to the Components item within the menu bar at the top of the screen and choose a component named Current. So right here, we have the component icon from the menu bar. It looks sort of like an AND gate. That's going to open up this menu right here, and we are going to choose a source, a component that's simply named current, and you can see the symbol here looks like that which we're familiar with to represent a current source. If you're having trouble seeing some of these pictures, you can download the source PDF, and I have higher res versions of all of these images that you can take a look at. I'm not going to click on them here, but you can do that on your own. Now, once we've placed our current source on the schematic, we must define its name and its value. This is done by right-clicking on various parts of the component as shown below. Note that our current source, as shown in figure 3, is placed upside down, and we're going to correct that in later screenshots. I didn't realize when I was building it that the direction was opposite of what we were looking for. All right, so how do we define the different values? So the first thing that I did was I right-clicked on the source itself, which brings up this box and allows us to set a DC value in amps for our current source. I'm going to go ahead and set it for 125 microamps. Now, We call this IS1. I want to rename it accordingly. So I right click on the name itself, which brings up a new box. Okay, and I can enter some text here. I'll enter IS1, and that will change the name that's displayed right here. Next, we can use the move tool, which looks like a little hand, in order to move this component to the appropriate place in the workspace. All right, next, let's place some resistors in order to set up the general structure for our circuit, and then we'll go back and place our voltage source. So, to place or to design with resistors, we choose the resistor tool from the menu at the top of the screen. So, this is a little bit counterintuitive because you may be thinking I should go to the components icon and then choose resistor from there. No, there is a separate icon for resistors, which you're going to choose, and then that will allow you to place as many resistors as you would like. And you can place them wherever is appropriate. The command Control R, so while you're placing a resistor, if you hit Control R, that will rotate the component. And this applies to resistors as well as sources. You have to do this before you place. You can still rotate after placement, but that's a slightly different process. Although it's not explicitly shown in the figure below, we must still use right-click to define the resistors' names and resistance values properly. The result is a schematic with the current source and the 4 resistors as shown below in figure 5. So, just like we did for the current source, we right-click on the component itself, and that's going to allow us to redefine the resistance. Then we right-click on the name, and that's going to allow us to redefine the name. You want to use Control R again to rotate the resistors, and right now you can see we haven't put the wires in yet, but we've got the general layout of our circuit there, minus the voltage source, which we still have to place. So next, placing the voltage source. That's the only thing missing right now is the voltage source, and we're going to follow a pretty similar procedure as we did before. We're going to go to the components icon, the one that looks like that, kind of looks like an AND gate, from the menu at the top of the screen, and then choose voltage. So you can see here, I chose voltage. It brings up something that looks very similar to a voltage source, and I place it right here. Again, I can use Control R in order to rotate it and make sure that the polarity is correct or the orientation is correct. All right, so now we have our circuit, but again, it's missing the wires it needs to connect everything together. So we need to place those wires. So once the components are placed, we use the wire tool to connect them. Now, this process is pretty straightforward. I mean, I could go through some really in-depth explanation of exactly how to click, but I think this is something you should be able to figure out, especially for anyone who's familiar with similar graphical user interfaces. If you have a problem, I'm sure you can find another resource online, but I felt like perhaps it might not be the best use of our time right here. Okay. Real quick, the wire tool looks like a pencil, and essentially you just click on one end and drag. It automatically makes the corners and the proper junction points. You can tell when 2 wires are connected because it'll make that thick dot. Anyway, as you can see now, our circuit looks how we expect it to look. So our circuit is done. We have our current source, our voltage source, we have our resistors. We're good to go. Now, there's one thing you can see here, which I guess I didn't do at the beginning, but we'll do later. I haven't defined the voltage value yet, and I also didn't redefine the name. So I think I do that later on, but if I were looking at this circuit right now, I would right-click here and rename this to VS5, and I would right-click here and rename it, change the value to 1.25 volts. Okay, one final thing that's missing. Oh, you can see I did do that below. Okay, so one thing that's missing is the ground. So all you have to do is go to the ground icon. That'll bring up the ability to place the ground, and you can see I put mine right here. All right, so we're done building the circuit. All the components are there, and everything has the appropriate names, and everything has the appropriate value. But we're still not done. Now we need to name our nodes, because otherwise it's going to be very difficult for us to understand any of the simulation results, right? We're going to be looking at a bunch of different voltages, and if we don't name them, how do we know what's what? So now that the circuit is complete, including all the components and connections, we can label the nodes referred to as nets within the LTSpice software. This process is, again, relatively straightforward. We must right-click on a node and choose the Label Net option. This allows us to choose a more recognizable, non-default name, such as Node A. That's what we're going to use, Node A, Node B, Node C, Node D. And so that will show on the schematic itself. If we do not define proper net labels, it may be challenging to understand the simulation results. So let's take a look at what we have down here. You can see here that I right-clicked on any node. So you don't really have to right-click like on this point right here. You can right-click anywhere along the line. And it will bring up a menu, which one of them provides the option of label net. Okay, once you click on that, it brings up a little text box, and you can put in the name. So you can see I labeled this Node A, Node B, Node C, and then this one I didn't have to label because it's ground. The nice thing that you'll see about LTSpice is it understands what nodes are electrically the same. So even though we haven't labeled this node, this junction specifically, it automatically understands that node C is electrically the same, or it extends to include both of those junctions. So you won't be able to provide conflicting names to electrically similar, or two nodes that are electrically the same and have the same potential. All right, so now we have a circuit where not only all of our components are labeled, all of our values are labeled, but also the node names are provided. So now when we simulate, we'll be able to tell what voltage and current corresponds to what. One other thing you can see, I did flip the direction of the current source, which I said I was going to do up above. I didn't do that till later. Okay, so now our schematic is done, but we still need to configure our simulation. So before we can configure our simulation and analyze the circuit, we must configure this simulation. Obviously, it doesn't make any sense. Before we can analyze the circuit, we must configure the simulation. So that's what we're going to do now. There are several simulation types from which we can choose, and they are listed below. This is a really interesting section right here, because even though we're not going to do all of these types, we're only going to focus on the DC sweep. This little blurb here will give you a good understanding of what the other types do. All right, so we're doing DC sweep analysis. It simulates the circuit's steady-state DC behavior with respect to one or more changing variables. In our case, like I said before, we're going to be sweeping for value IS1 and looking at the outputs of VA, VB, and VC. So this is going to be our independent variable, and this is going to be our dependent variable, and we're expecting to see sweeps which tell us how VA, VB, and VC change when IS1 changes. All right, so for example, in this tutorial, we're going to examine how the node voltages evolve as IS1 changes from 100 to 150 microamps, and 125 microamps was the nominal value that we calculated or will calculate a solution for when we do nodal analysis. All right, there are several parameters of this type of sweep which we need to understand. We have first or more sources, Okay, this defines the different sweeps to be performed. We're only going to be performing the sweep along a single variable, so we'll only have one first source. Okay. Type of sweep defines how the independent variable, which is IS1 for this tutorial, is incremented. A linear type sweep increments or increases the independent variable at regular intervals, but for other types of studies, you can increment with a logarithmic pattern, which the increments are not going to be even, but are going to increase exponentially. We have start and stop values. This is the range of the sweep in terms of the independent variable. So for our analysis, we're going to be using 100 as the start value, 100 microamps, and 150 microamps as the stop value. Then we have the increment, which defines the increment of the sweep. The total number of data points generated will equal the stop value minus the start value divided by the increment. So like, let's say, for example, we wanted to find this number. We're going to have 150 minus 100, this is all in microamps, divided by, let's say that we set our increment at 1 microamp. Okay, then we would end up with 50 data points. All right, so that's DC sweep. It's relatively easy to set up. You have to tell PSpice or tell LTSpice what source you're going to be sweeping, what type of sweep you're going to be using, what the start and stop values are going to be, and by what you're going to increment, or by what value you're going to increment. Next, we have transient analysis. So these two analyses right here, these are the ones that unfortunately we're not going to be diving into. Transient analysis, as the name suggests, simulates the circuit's behavior with respect to time. So in other words, it's going to display what you might see if you actually were looking at the circuit on an oscilloscope. This type of simulation is generally applied to the analysis of transients, obviously, or irregular steady-state oscillating waveforms. So whenever you have a value of interest with regard to how it changes with time, you would want to use transient analysis. One must define the start and stop time of the simulation, as well as the maximum step size temporally, which dictates the precision of the analysis. We also have AC sweep analysis, which is essentially the same thing as DC sweep, except you can use an AC value as the independent variable. So if we were to build the same circuit that we have here, except our IS1 were an AC current output, then we would use AC sweep to vary the amplitude of that, or to vary the frequency of that. Now, there are some other simulation types which we're not going to talk about here. You know, these SPICE tools are very powerful, and I don't want to really overwhelm anyone. So let's start off with this fundamental look at DC sweeps, and then hopefully, like I said, it can be a good jumping off point for more independent learning. All right, so now we need to configure our DC sweep. We already know what values we'll need to define, and we know what they are. We're sweeping IS1. The sweep is DC analysis, linear type. We're going to be going from 100 to 150 microamps, and I don't know what the increment value is we're going to use, but we'll see it down below. Okay, so we're going to click the Edit Simulation command from the Simulate menu in order to configure our simulation and create what's called a simulation profile. So the simulation profile is, as the name suggests, a profile, a description of how your simulation is going to operate. So the figures below demonstrate that we utilize a DC sweep, which will vary the source from 100 to 150 microamps with an increment of 5 microamps. So we're only going to have 10 data points. The result, will be 10 data points with an even distribution between the minimum and maximum values of the sweep range. So let's take a look at what we have right here. Okay, we go to Simulate. We go to Edit Simulation command, which is how we edit our simulation profile. We click DC sweep. Right here, I put IS1 as the name of the first source to sweep. then I choose a linear type analysis, linear type sweep from the drop-down menu. I put in the start value as 100 microamps, end value as 150, and increment as 5. And then I just click OK. And you'll see that unlike some other simulation packages, this actually will display these values on the schematic as a simulation command. So you'll see these values displayed. All right, now that our simulation profile is ready and we've created our schematic and we've labeled all of our nets, we're ready to run. So we're going to go ahead and click the run icon, which looks like a little running man. And that's going to start the simulation. And it should automatically bring up a display screen with the simulation results. So you can see the little running man right here. That's the run command. This is just what the simulation parameters will look like when they're displayed on the schematic. And once our simulation is complete, it's going to bring up a blank set of simulation results. So you'll see here on the x-axis that although it's too small to see, it's going to range from 100 microamps to 150 microamps on the x-axis. The y-axis will be unlabeled because it doesn't know what to show us yet. We haven't told LTSpice what values we're interested in. That's the next thing we have to do. So why are there no traces displayed in the graph on figure 12? Well, that's because we haven't placed any probes yet. This is very similar to a laboratory experiment, right? It doesn't matter if you've built a circuit and have it running, but if you haven't connected any probes to it from your DC oscilloscope or from your digital multimeter or from your oscilloscope, then you won't see anything. So we need to place our probes. We can place a voltage probe by clicking on the node in the bottom half of the screen, showing the schematic. So this is a little bit different than the way some other packages work, where you actually have to choose a probe tool from the menu bar. We don't have that here. You essentially just click and it's automatically going to place a probe. If you want to place a current probe, you actually click on a component. The current probes they lie within a component. Okay. Now, the traces should already be labeled, or the nets, the nodes, should already be labeled according to those that we provided above. So the voltage and the current measurements should automatically be labeled in a way that we recognize. One may click the colored trace labels at the top of the graph to see data with greater resolution, and this will bring up a window that displays the actual data values. So you can see here that we clicked on one of the nodes, and now there is a sweep result displaying on the top half of the screen. If we double click on that label, as shown right here, it'll bring up a window that looks like this. This window allows us to read exact values. So let's say we wanted to see exactly what the corresponding voltage was when the current is 125 microamps. So what we can do is use the mouse to go back and forth, wait until this equals 125 microamps, and then see the exact voltage value. So that's very useful if you're trying to, like I said, get more detailed values. And all we have to do in order to see all the values is just place more probes, and it will automatically assign colors to those individual probes. Again, I know some of these pictures are small, but you can download the PDF from the video description. I encourage you to do that and follow along, and then you can use these high resolution links in order to see the pictures with greater detail. Now, let's say you need the data for some other type of post-processing analysis. Fortunately, LTSpice will provide an Excel file, a comma-separated value file. So if we need a more detailed look at the simulation data, we may export it as shown below. We choose export data as text. We choose the traces to be exported with the appropriate labels, and then we can open this CSV or TXT file in Microsoft Excel and use tab delimiting to display it with appropriate columns. So let's take a look at that process right here. You'll see under File, there's an option for Export Data as Text. That'll bring up this window right here where we can choose which voltages we want to, or well, there's currents as well, but which values you want to export. Now, the nice thing here is look at the way these are labeled, right? I haven't really taken a good look at this yet, but look at how nicely they're labeled. It's very clear what everything is, right? You can see that this is the voltage associated with node A, this is the voltage associated with node B, this is the voltage associated with node C, and then you can see the current flowing through R6, through R4, through R3, through R2, and through the sources themselves. So if you label your components properly and you label your nodes properly, then this data should be very easy to understand. And then this window right here is simply just, this is actually not from LTSpice, this is from Excel. And this is the window that you use when you open a CSV file in order to split it into columns. And so you can use tab delimiting or comma delimiting depending on what the structure of the file is. And this will provide us with a nice looking table, which we can use how we wish. Fortunately, we see that our simulation results match that provided by Nodal Analysis and discussed in the introduction section. So you see right here, we had already solved for the values of VA, B, and C for the case where our IS1 is equal to 125 microamps. So you see 125 microamps right there, and then we have three additional values, VA, VB, and VC. I'm not going to scroll back up right now, but these values, 783 millivolts, 767 millivolts, and 1.25 volts, they match that which we calculated above. In conclusion, this, I feel like a broken record, is really just a jumping off point. There's still, in order to fully understand LTSpice and other packages, there's a lot of work that you would need to do. However, at least now you understand the basics of how LTSpice and really in general how other Spice software work. If you understand how to use LTSpice and then you jump into something like Cadence or CAD, it's not going to be that different. Now, the buttons are different, the way that you set up the simulation profile is different, but overall the basic gist is the same. There's the same types of sweeps, there's the same need to place components, to place probes, to place grounds, to define your node names, so all the same steps. So hopefully this tutorial will help you begin your exploration with Spice simulation tools like LTSpice, and I think we did a pretty good job of covering the basic skills that you need to begin that journey. I've provided some additional links here that you should check out. Fortunately, LTSpice is a piece of software with almost an infinite, limitless source of online tutorials that go into much more depth than this one, so I encourage you to refer to those as well. Good luck.